Alright, hell yeah. So we have physics, and what we have is this teeter-totter, you know what I mean, seesaw. And this is an example in this book. This book is actually, one of the versions is online, so in the description, maybe I'll try to link you to that. So then you can kind of see what the example is. But what I'm going to learn, you know what I mean, is rotational inertia, if it kills me. I feel like it's it's too complex. You know, I mean, how do we make it simple? And then I want to be able to, pick apart something and be like, well, can't we just make this simple? So at the end of the day, we have father-daughter. That's kind of the setup. And I'm just going to put some weights on this. We're going to do mass, and they do MF for the mass of the father, and then MD, mass of the daughter. I'm just going to say, in the book, they don't put values on this. I'm just going to say 100 kilograms. You know what I mean? That's 220 pounds. You know what I mean? That's pretty significant. And then I'm just going to do half over here. So we got 50 kilograms. You know what I mean? 50 times 2.2. 110 pounds. Okay, so yeah, that problem's legit. And then and I'm just going to put them just kind of balanced. So here's our pivot point. And then we're just going to do an angle of 0, and we're going to analyze that. And so we're going to do a couple things, because I think it's just really good. So we're going to take that 100 kilogram. We're going to take the mass of the father. This is 100 kilograms. And we're just going to put it in free fall. So we're just basically, what we're doing is making our own free body diagram. It's not the free body diagram of this, but we're just going to put this just up in the air, and we know that it does have a weight of MFG, and you know what I mean, like all my videos, we anywhere where we can, we analyze where the hell all this comes from. So this is, the weight is a force of gravity. So we're saying, hey, that's a force of gravity, you know what I mean, of the father. So the equation for force of gravity is Kepler. You know what I mean? It's a gravitational constant. Mass 1. You know what I mean? This would be the mass of the father. Mass of the earth. You know what I mean? Maybe capital M-E. And then radius of the earth squared. But what you'll find is that these three terms will just add up to 9.8 meters per second squared. And then because I really like to solve physics from the standpoint of F equals ma. Even if it's an energy equation. Cool, energy equations are very useful, but I think what you do is you fall into the trap of just not having a fundamental understanding. I mean, I think if you're losing the fundamental understanding of F equals ma, then from my perspective, you lose the gist of the simplicity of physics. You know what I mean? This relationship between, hey, force and motion is very fantastic. So anyway, so in this equation you got two parts. Now these are vectors, or you could write them as sum of the forces is equal to mass times sum of the acceleration. Hey, you could mass could be a vector, but we know that mass basically anywhere in the universe, unless you're getting into some Einsteinian stuff, is basically all the same. But your forces will change, your accelerations will change. Okay, so, and then this is the mass that we're trying to analyze. So, okay, so we have F equals mass of the father, and then the acceleration. So we want to know the acceleration, and we want to know what forces are being applied. And so I consider this, eyeballs on this side, like so if someone is just, like, hey, they stepped off a cliff because they're going cliff diving, well, cool, that's what we're analyzing right here. They have initial velocity of 0, but we know from experiment that they will hit at a pretty decent velocity, you know what I mean, maybe Vmax down here. And so in general we see a change in velocity. So that's this side, acceleration. We're going to see a change in velocity. Alright, so I'm back, set my timer. And so why are we going over the basics, at such a basic level? Well, it's because I tried to set this up with, and you'll see in a moment, like how I set this up. And I guess we can just get there, a little foreshadow. So I'm just like, well, if you have a teeter-totter, it isn't, like, well, I just say, hey, if you just have this in free fall, Holy Toledo, you're going to be accelerating. We know this is crazy. You know what I mean? You jump off a 3-foot, perch, you're gonna hit the ground real hard, and that would suck. But we know if we have some sort of weight on the other side that's fairly balanced, like, whoa, we're not moving very fast at all. And like we can control that. And so what I did is just like, well, let's do a pulley. And then, so we have the smaller mass over here, the bigger mass over here. And but even in this, like there's a couple places where I'm just like, if I don't come back to this within every 10 years or so, then I just make bad assumptions, because it's just like, well, isn't this just if this is the bigger mass, this is half this bigger mass, isn't that just like saying, well, you have a just a half this mass just in free fall, like it jumped off a cliff? No, you know what I mean? So so that's what we're going to be tackling. And then even after that, there was one more hiccup that I ran into, and it comes out with analyzing. What the hell are you analyzing? So you have F equals ma. We're analyzing right now this mass right here. And then so we know we have acceleration. We want to find that acceleration. So this side, well, it's like, well, we need to figure out what forces might be on it. What forces in the known universe. And so we go to our textbooks and we're like, whoa, there's a huge Earth underneath us. That's important, because now we have a force of gravity. And then we find in our books that this is the force of gravity. This is the relationship between two masses being, at some distance apart. And heck yeah. And so we can throw this whole thing into this side of the equation. So you got G, mass of the Father, mass of the Earth, radius of the Earth squared. And now this side of the equation is what we were analyzing. We were analyzing the mass of the Father. So mass of the Father, acceleration. So now if we want to get acceleration as its own equation, we have acceleration, or just the acceleration at this moment. We have acceleration is equal to, well, you're going to bring the mass of the Father downstairs, and then you're going to cancel it with that. So you're just left with those three terms: gravitational constant, mass of the Earth, radius of the Earth squared. And if you do these, this is 10. This is 10. It's 9.8. And it's a good one to memorize, because this is 6.66, just think the devil, and then negative 11. And then this is 6 times 10 to the 24, just think more, science is of the devil. And then, holy Toledo, radius of the Earth is 6 times 10 to the 6 meters, 6 million meters. Holy Toledo, this is Illuminati stuff. Anyway, but you have this 6 squared. So so this, you can write it as 36, or you can just write it as 6 times 6, times 10 to the 6. Yeah, we're doing pagan worship now. So anyway, and then so this 6 will basically cancel that 6. This 6 will cancel that 6. And this 6 got squared. I apologize. So that becomes 10 to the 12. So now how the hell all this can be 10? Well, this 10 to the negative 11 is up top. So that's the same thing as 10 to the 11 downstairs. And then you add 10 and 11 and 12, and that's going to be 10 to the 23 downstairs, 10 to the 24 upstairs, and booyah, you got 10. You know what I mean? So it's just really good to go over the basics to see where all that crap comes from. So now we found that, this free-falling cliff jumping has an acceleration of 10. Cool. Now, when we throw it onto the pulley, I swear, my mind melts. So this is the problem that we're going to analyze. I should have had a picture of it, but hell yeah, we have a really lightweight pulley. Pulley is massless, you know what I mean? And then the string is massless, you know what I mean? So the only two weights are going to be the mass of the Father and then the mass of the daughter. And we know that this is 100 kilograms and this is half, 50 kilograms. So now we can do our free body diagram again. And what I do, because free body diagrams suck, so we're gonna basically dot whatever you want to cut out from the thing that you're doing, and then I like to say cut out of outer space, because everything is in outer space. You just don't think it is, because you're just like, well, I'm close to creature comforts, and but nah, you cut yourself out like this, free body diagram. you're literally alone in the universe. So there you go. So that's what we're going to do. And we're going to do two things. We're going to assess, yeah, sure, this did have a force on it. We still know there's an Earth underneath, that if this is a mass, it's going to have a force on it that's called its weight. That's the mass of the Father, G, mg. So what did we solve for over here? We solved for the acceleration was just this, which was 10, and that's what we're calling g. So we're calling the acceleration g, and that's 10. So now we can go back and well, and then the other thing, if we just wanted to find the force, obviously those three things were just 10, and yeah, I guess this problem was to figure out the acceleration of gravity is 10. Cool, we got that. Or you just use this equation straight up. This is the force of gravity. And then so you can say, hey, this is the mass of the Father, g me, radius of the Earth squared. That's the same thing as the mass of the Father times g. So there's your force of gravity. I apologize that I kind of always end it at, hey, finding the acceleration is 10. But no, it's just like this is when people write, hey, we have a weight here that's mg. Well, they should also be saying, hey, this is just m GME radius of the Earth squared. So that's what you can also type in right there, and then you know where that comes from. Okay, so from our little setup, we do know that the Earth is underneath this mass and it's going to pull down with 100 kilograms. So that's what we have. We have a weight that's mg. That's going to be 100 kilograms times 10. That's going to be the mass of the Father times g. And now up here, I guess you just have some sort of tension. And this is the first kind of mistake that I made. Is just like, well, I mean, couldn't you just assume? And it's not. You can't do that. Couldn't you just say, well, isn't this just 100 times 10? Mass of the Father times gravity, and isn't this tension just 50 times 10, the mass of the daughter pulling the other direction? And no, and it's because. So I don't mean to answer this question right here. I mean to get stumped and then find other ways. But no, this is because what you're saying is. What you just want to do is analyze maybe how much is this going to move. We want to find the acceleration of this situation. Now you could do this. You could say, hey, I'm 100 kilograms. So I know that my weight is going to be 100 kilograms times 10 or something like that. But now I have made a force upward. Maybe it's a little rocket. Maybe I got those like little cool jetpack on. And and then I know that force can generate 50 times 10. You know what I mean? And this, what the hell is 100 kilograms times 10 meters per second squared? This is 1,000 newtons. So this is how much you weigh in newtons. And then this would be 500 newtons. So in this case, sure, I could jump off a cliff and I would have 1,000 newtons of force. And what the hell does that mean? Force is equal to mass times acceleration. So my acceleration would be 1,000 newtons divided by my mass, 100 kilograms, is equal to my acceleration, which would be 10 meters per second squared. And what does that mean? Well, it means 10 meters per second per second. This means the definition of acceleration is change in velocity, change in time. So this says, hey, in the first second, I'm going to increase my velocity from 0 to 10 meters per second in 1 second. Okay, cool. But if I have this little jetpack on that can only generate a force of 500, that can only generate a force of 500 newtons, this little jetpack, well, then my, it's, now I gotta take a pause. So what are we doing? We're saying in this scenario, because we want to analyze that scenario, even though it's not this. This is different. And and I'll just get to it. The reason this is different is because you don't just have 100 kilograms here. You kind of have to like cut out the entire system at some point and say, no, this system is 100 plus 50. This whole system is 100 and 150. You can do this, you can chop it out, but we just have a force. You cannot just assume that this force is 50 times 10. You know what I mean? The other mass. That is something you can't assume. You can with the free body diagram, you can be like, hell yeah, there's a tension there. But you just don't know what that is. You can't just assume it's that. Because this tension, and another foreshadow, just to make, kind of get to the points a little faster. If, because we can also do like the bridge. Well, I don't even know where I'm going with this. Let's take a pause on that. So we're going to do this one, and because I think I'm stumped on this. We got F equals ma. So I'm analyzing this mass. This mass is what I'm analyzing. This mass has a mass of 100 kilograms. Cool. And now this side is like, hey, I'm trying to figure out from the textbooks where the forces are. So I do know that there's a force of gravity. We already got that. We have an earth underneath us. But now I also know from the textbooks that little rocket engines, you know what I mean, provide force. And so, and I can calculate that. And so from this rocket, another out of the book, so I know that this side of the equation is going to be 100 times 10. That's my mass times gravity. And that's going to be, I'm just going to say this is the positive direction. Cool, because that's the direction we're interested in. I want to know my speed down towards the earth. That's important to me. I'm going to call that positive direction. But then we have a force that's in the opposite, so we're going to go negative 50 times 10. Okay, so now those are the forces, and now over here, I still have mass times acceleration, and this mass is still 100. And so now, because when I have this, and I don't know why I'm going over this to be like, well, because I made the mistakes. As sometimes I will make this mistake and be like, well, if I have 100 kilograms right there, and then I have a pulley on me that's 50 kilograms, isn't that just the same thing as 50 kilograms in free fall? And it's obviously no. But I mean, but only if you've played around with pulleys, you know what I mean? And you've had like a weight over here that's heavy and a weight over here that's not. And, and you're like, oh, okay, this thing isn't moving that fast. It's not moving in free fall, you know what I mean? And here's why. Because you had this weight force, but then you subtracted some other force, that was the jetpack, but now you're still analyzing just the 100, you're still analyzing the mass. So you have this equation, F equals ma. So yeah, your forces can be anything, but you're still analyzing the mass that you chopped out of the free body diagram. You know what I mean? So that's what we're doing. And then so, in essence, this equation, if you wanted to find the acceleration, is just, well, divide by mass. So you have the sum of the forces divided by the mass. Doesn't matter what the forces are. Those are just all out of textbooks. And they give you a number in newtons. And if you have a force that way and a smaller force this way, well, then you have a net force that way. So that's what we're interested in. So this acceleration is also just whatever the net force is divided by the mass. And so that's what we have down here. Sorry for writing so small. But now we can see just by, hey, this is 1,000, this is 500, so that's going to be a total net of 500. And now we're going to divide by 100. So we have 500 divided by 100. Our acceleration is 5. So that's what we're comparing with. This whole video is going to be like, hey, acceleration of gravity is 10 meters per second, change in velocity of 10 meters per second. And if you want to multiply by 2.25, you know what I mean? Multiply by 2, but 25% tip. That's how I like to remember it. It is going to be 22.5 miles per hour every second. So holy hell. That means in 2 seconds you're going to be going 45 miles per hour. So hopefully when you jump off a cliff, you're only in free fall for less than 2 seconds, or 2 seconds max, because 45 miles an hour, that sucks. and you want to be landing feet first, and maybe got some shoes on. So a 50-foot cliff, I thought would generate about 50 miles an hour. Don't quote me on that, but cool. But now we're saying, no, for this pulley, or this scenario, you know what I mean? This pulley, the tension is going to be different. So yeah, foreshadow there, that's fascinating. That's fascinating to me. It's because you have a continuity and you have to take the whole thing into consideration. Yep, I thought it would be related to a bridge. I do this a lot. If you have a bridge, you can put the mass here. Like, hey, there's no force over there. Or you can put the force here, and there's no force. You can put the force in the middle, and it's halvesies. You know what I mean? Or you can put the force over here, and it's more over here. Maybe 3/4, 1/4. That doesn't apply. I don't think that has a direct correlation to what we're getting after. Okay, but now we know that, yeah, if I jump off a cliff, but for whatever reason have some cool force that's opposing, like gravity, you know what I mean, the force of gravity, which is this is the force of gravity, then hey, I'm not falling at 10 meters per second or 22.5 miles per hour every second, you know what I mean? 10 meters per second every second. That's acceleration. But no, it's less, which is cool. That's why teeter-totters work, because, hey, if you're up 3 feet and you fall like a rock and fall off the teeter-totter, oh, that's going to suck. But as long as you have some sort of balanced, like reduction and just some sort of difference, then you're good to go. Now, there's a point where if you don't have any weight over here, just the weight of the seat itself, no other person, and then you go up and then you're like at 3 feet and then fall to the ground, heck yeah, on your butt, that's going to hurt. You have to have some sort of weight, you know what I mean? So it would be like this. If I have 1,000 newtons, that's our weight, 1,000 newtons down, but I only have like 100 newtons opposing. Well, now I'm going to have 1,000 minus 100, 900. Now I'm going to have 900 divided by 100. I'm going to have an acceleration of 9. Still hella sucky. You know what I mean? Now, you know, so just any fraction of g. So it's good to get used to problems where you're like, yeah, 10 meters per second. Hey, that might suck. You know what I mean? That's standard, or that's just gravity. You know, that's a g force of 1. And now, if you have 2 g's, hell yeah, that's way suckier. But if you get down to like, oh, our acceleration is only 1/2 gravity, you know what I mean? Hell yeah, maybe that's something. That's not too bad. Not too bad. Okay, so that's what we're going to analyze. And I need to get a new sheet of paper, and now we're going to figure out why this tension isn't just the other weight. You know what I mean? I think that's the first place to go. So we have the mass of the father, we have a pulley, and then we have the mass of the daughter. And so let's do, so how to make the most sense of this is to, you can do free body diagrams, you know what I mean? Because obviously this one, this is the weight is mg, mass of the father, gravity, cool. And then we have some sort of tension. And then the other one, we have the mass of the daughter, which is mdg. And then guess what? The same tension. So there's kind of our first continuity. Is like, hey, these tensions have to be the same. And that's cool. But we're going to do this problem 2 different ways. Because even from right here, oh, this is hella sucky and complex. Because this tension is the same as that tension, but the directions are totally different. This is accelerating in that direction. This is accelerating in this direction. It's just totally screwy. So anytime that you have a problem that has like a continuity of a path, alright, hell yeah, I had to take a little break, but we are back. And we're getting, well, I'm kind of showing you one way to make something that has like a path where you know what I mean? What we're showing is like every part of this is connected. And so if this moves, you know what I mean, that much, hey, this has to move the same amount. And so we can take this thing. I just thought this was a neat way. I'm going to bring it up here. So I'm going to take this, and then we have our string. And then so, heck yeah, this is what we're going to do. and now add the forces back in, but not the tension. Because now this is very similar to a bridge. I don't know why I go back to the bridge analogy and just like mess up every time. Holy Toledo. I don't think it's going to be similar to the bridge. Oh yeah. Because with the bridge, you can do the free body diagram. So we're going to put like a weight. You know, usually you see that, a weight piece. So if you do the free body diagram of the entire thing, or I think you would do, maybe you would chop out. Oh man, maybe just the bridge itself. So if you chop out just the bridge itself, heck yeah, you got a load there, and then you got these two loads there and there. And as long as this is centered, that these are going to be equal. Damn it. But anyway, let's go back to this one. I don't. Yeah, I keep bringing up a bridge, and it's not helping at all. But okay, so this was the direction of the force of the weight, so then we got to throw that in there. So we got to go, hey, this is mass of the father times g, and then this was the direction of the weight of the daughter, mass of the daughter times g. So that's this direction, mass of daughter times g. Cool. Oh, well, yeah. But in this free body diagram, we cut out the entire thing. So I guess that's what I'm getting at. Cool. Yep. Okay. So and that's going to be that way. But you don't like the tension is in the chord. You actually don't include holy hell. Am I getting messed up on my own problem? No, I think we're still good. Because, yeah, the tension isn't going to be in the chord. Okay, hell yeah. Okay, yeah. But yeah, it's just, I don't know why that's why we're doing these videos. Because it's just, hey, I just chopped out that weight. You know what I mean? Hell yeah. I had 100 times 10, mass of the father times 10, and then chop out that one, do my own free body diagram over here, mass of the daughter, 50 times 10. But the second you chop out the whole darn thing, you have to go back to F equals MA. So sure, and I think it relates to doing a bridge where if you just chop out that point, you know what I mean? So now we, oh man. Yeah. But anyway, let's not bring up the bridge. No, we do have to bring up the bridge one more time to actually show what's going on with the teeter-totter. But so yeah, so we have our F equals MA. Well, guess what? What are we analyzing right now? We're analyzing the whole mass of everything, the whole mass of the system, and then that's what we're trying to find the acceleration on. Because down here, sure, the acceleration this way, we can do the same thing. F equals MA. We sum the forces, and we said, you know, we have this mass of the father G, and then we have minus the tension, and we probably know that the acceleration is going to go that way. And that's going to equal, well, what mass are we analyzing? Well, that's the mass of the father times A. So in this case, we're going to have an equation for acceleration that's mass of the father G minus T divided by mass of the father. So there you go. This is the acceleration. And it's going to be the same acceleration for doing the free body diagram over here. We're going to have F equals MA. What the hell are we analyzing? Well, the mass of the daughter. So we can find the acceleration of the daughter. And we can say, what are the sum of the forces? Well, we have M, mass of the daughter, G, minus T is equal to mass of the daughter, A. And then rearrange and get acceleration is mass of the daughter, G, minus T, divided by the mass of the daughter. Cool. And what we're going to find is that this equation is equal to this equation is equal to this equation. So now we have the whole system, and like we said, you know, they're perfectly connected, where if this one moves, that one moves. And this is the F equals ma that explains that. But now our mass, the mass that we're analyzing, is is the whole system. So now we find the forces, and we say, sure, you have mass of the father, gravity that way. You know what I mean? Minus mass of the daughter, gravity that way, is equal to, well, guess what? What mass are we analyzing? The whole system. So this is where mass of the father gets added to mass of the daughter, and then we find the acceleration. So we rearrange that equation for acceleration, and we get mf. And then we can factor out a g. So we can go g mf minus md, and then divided by mf plus md. Cool. And then so here you get the actual acceleration. And that's going to be the same. And guess what? This doesn't have tension in it. This just has things we know. We know the mass of the father, mass of the daughter, mass of the father, mass of the daughter, and g, so we can find that. So actually, you don't even solve for t first in this one, the way that I did it. And then we can go back, and from this acceleration, we can put it into there and find that tension. We can put it into here and find that tension. So let's get these equations for tension, because we're gonna multiply that upstairs. Mass of the daughter times acceleration, and then we're going to minus mass of the daughter times gravity. That's going to equal negative t. So I'm just going to say t is equal to there you go. And then over here we're going to have mass of the father times acceleration minus mass of the father g. So I brought that upstairs and then brought this over. But then that's going to equal negative t. So I'm just going to say t is equal to negative there. I distributed the t through. So now we'll be able to find the tension. And heck yeah. So right here we're going to have 10, just real easy. 10, 100 minus 50 divided by 100 plus 50. Cool. So now we have 10, 50 on top divided by 150. So here is kind of what you see. 50 divided by 150. That's a third. So now we have a 10 times a third. And you get 6.66 repeating. Holy Toledo, 3.33 repeating for our acceleration. Our acceleration is this many meters per second. You know what I mean? 3.3 times 2.25. So every second you're going to be going 7 miles per hour. You know what I mean? With that acceleration. Okay, so we're going to take 10 divided by 3, stored as a, and now we can throw it into here. This is going to be negative 100 times 3.33 plus, this is 50, sorry. Mass of the daughter, 50 times the acceleration, plus 50 times 10. So we have 50 times 10 minus 50 times 10 divided by 3, or 3.33. Okay, sweet. So now we have a tension, and I feel like I did this totally wrong. No, I didn't, because, okay, let's get a check on reality, because this tension's coming up as 333, and I recall when I was actually doing this problem, I think I made a huge, I get the mistake that I made. I thought I considered 100 kilograms to be 100 newtons. That's not the case. The newtons on here is 100 times 10, so we would have 1,000 newtons. And let's just get a check on reality using some of those bad techniques of being like, well, if I have 1,000 newtons down, but then my tension up is going to be 500. You know what I mean? And then I thought I had... So there you go. So I thought I had 1,000 newtons down, but in this case I thought the tension might be, you know what I mean, this 50 times 10, 50 kilograms times 10 meters per second. I thought it might be 500 up. So I thought my tension might be 500, but it's not. It's 333. Okay, so let's solve right for this one, and we get negative 100 mass of the father times 10 plus 100 times 10. How the hell did this one get messed up? Oh, weird. Oh, whoa, whoa, whoa. Yeah, my bad, my bad. Shoot, this is the acceleration that we just found. This is the 3.3, you know what I mean? This is why, you know, if they're balanced with something, hey, you're not just in free fall. So yeah, sorry, this is 3.33, and holy Toledo. So we have 100 times 10, and then we're going to subtract 100 times that 10 divided by 3. Cool, and this tension is 666. So that's what I thought. I thought I have an error here somewhere. Why would I have an error? Yeah, what the hell did I do wrong? Alright, this is where I pause the video for at least 5 seconds, because you don't want me to just scratch my head. Oh, okay, yeah, we're back. Alright, so yeah, this is the crappy part about these problems, is that, hey, this one is going to accelerate in that direction, and then this one is going to accelerate in that direction. So we just, I thought this would cover it, you know what I mean? Well, at least we figured out, this at least figures out your acceleration. I mean, you can get the acceleration. Now we just know that it's going this way. And so if we're saying the acceleration is 3.33, you know what I mean, it's going to change velocity every second, you know, by 3.3 meters per second, 7 miles per hour, that way. So we go back to our problem, well, it's going to accelerate this way. So if this block's going that way, that block's going up the other way. And then so we have to get that into our equation. So let's rewrite this equation. So we have F equals ma. We're going to sum the forces. But now what direction are we calling A? You know what I mean? Are we calling A positive? Because if we're calling A the positive, and then that's the number that we want to put in, 3.33, then we have to say, hey, this is the positive direction. So now your forces, you have a negative mdg. The weight is opposing that. But now you have a plus, a tension. Hell yeah, you have a tension in the positive direction is equal to the mass of the daughter times the acceleration. So now your tension is going to be the mass of the daughter times that acceleration. That's the 3.3 minus the mass of the daughter times, I'm sorry. Whoa. Plus, see that this becomes plus the mass of the daughter times g. So there you go. So now here's tension. Now you're going to have 50 times 3.33 plus 50 times 10. So you're going to have 500 plus a very small portion. I mean, this is essentially 100 times 1.5. You know what I mean? So you're going to have 50 times 150. You're going to get about 650. So that's the, and then yeah, we're 666 for the actual answer. But yeah, my apologies, but that wasn't too bad. You know what I mean? I think you're going to get messed up every single time on this because, hey, your acceleration is negative. We found the acceleration of the system linearly, but then when we went back, all we had to do, the one that we messed up for this one, was just change your acceleration to negative. So we have negative 50 times negative 10 divided by 3 plus 50 times 10, 100% confident that should come out, hell yeah, 666.6. And that's where when I got tripped up, no, I was tripped up right there. That I got to get better at being like, you have to teach your gut to be like, hey, I think something's up. I don't know. Maybe I'm just going to put like a star up here. You know, even in a video, you know what I mean? Hey, the second I feel like a number is wrong, you know what I mean? Do something to be like, you know, because you'll just explain that away. I swear, every mistake that you make, you're just like, nah, I'm just going to explain it away. Yeah, it's really interesting because sometimes you don't know the answer. You don't have anything tangible to go on. So the answer you get, you have no idea if it's right or wrong at all. Okay, so hell yeah. So we did that. And compared to the dumb way to do it is just like, well, don't we have 100 times 10 for you know what I mean? And then don't we have a tension of 50 times 10? So that's what we thought. We thought we might have a tension of 500. No, we have a hell of a lot of tension. And then because, you know, well, let's go back to that. Because we thought we had the bigger mass and the smaller mass. And the mistake I was making was, hey, this is going to be 100 times 10. I'm just going to say that's 1,000. And then I thought the tension would be 500. And then over here, I thought I would have 500 down, but then I would have a tension of 1,000 up. You know what I mean? And that's not the case because we have continuity. Well, it's not even continuity. It is because the mass of the whole system, it's F equals ma. And you have to analyze the mass of the whole system. You can't just treat this tension. I mean, you can't just explain it away and say, oh, well, this tension is just going to be the mass of that because that's being pulled down. No, because we did the rocket ship in analogy. If you jump off, mass of the father, but somehow you have like rockets underneath you, and you do have a force of the rocket at 500 newtons, sure. You know what I mean? Your mass down, your force down is 1,000 newtons, and yeah, you could find a way to get 500 newtons up. But in that case, your F equals ma. You're still mass of the father. That's the only thing that you're analyzing. Where, yeah, it's just fascinating. Where if you have a string and something pulling on you, well, now you just increased your mass. Sure, you developed a force, but you just now increased your mass, and so that's fascinating. That's actually really fascinating to me. Where it's just like I think there's more that I could run with that. You know what I mean? Because you get this force. It's not a rocket. You get this force, but at the expense of having another weight on the other side. So yes, that's interesting. And no, I find this very fascinating because the tension's even more than we thought. You know what I mean? Hey, we thought if we just put, we were just trying to get 500 newtons out of here, but yeah, we thought that would just be a force of 500, and then our acceleration would be 5. You know, in that case, if this just pulled 500 newtons and we're 1,000 newtons, then our acceleration would just be half. But what we're finding is no, the tension is a lot more hella, and our acceleration is a lot lower, 3.33, because now that force, and it is still true. You still are well. Could you say that? Yes, I think that this explains it. You know what I mean? We can still do it like this. You know what I mean? Where you can say, I'm sorry, I'm running out of but yes, let's do it. We have 1,000 newtons, and then sure, you have 500 newtons pulling you. I think this will work. Okay, so that's your total force, and you have 500 newtons. But guess what? That's acting on a mass that's way more than just this 1,000. It's not 1,000. It's a one. I'm sorry. It's not 100. It's 150. So now we have the acceleration is so if we do the equation for acceleration, it's 500 newtons divided by 150 kilograms, and a newton. Just in case you get bummed up on the units. You know what I mean? Go back to F equals ma. 1 newton is a kilogram meter per second squared. So anytime you see newtons, you can just insert kilogram meter per second squared, divide by kilograms, and hell yeah, now you get acceleration. So 500 divided by 150, and you get that 3.33. So yeah, you can kind of explain it that sure, this does put, it's just like, you can say, sure, I have a force of 1,000 newtons down because gravity is acting on me, and then I have a pulley over here, that's going to be a force of 500 newtons acting the other way. But now this whole mass of the system is no longer just this 100. It's connected to the other, so it's 150 kilograms. So that is a bizarre way to do it. You can't just take a free body diagram of this. No, I mean, you can. A free body diagram just says, hey, what are the forces? You know, it just shows the forces. Then you actually have to, and yeah, because when you do the free body diagram, you say you have a weight down of the mass of the father, G, but then you have a tension up. And then this, if you're analyzing just that mass alone, then yeah, F equals ma. The mass of that, and the resultant forces on it. So sure, this tension is going to be 666 because of that. Oh man, but anyway, I apologize for now just getting a little bit confusing. But hell yeah, I think we did it, you know what I mean? And I think I can make that a little bit simpler. But now we're going to use that concept to move on to the actual problem itself. It is rotational, rotational problems. You're using I. This is moment of inertia. And even me, I just have to get, back to the basics of like, well, yeah, this is moment of inertia. It's also called mass moment of inertia. So just write down, what the hell is a moment? Well, a moment of a force is force times distance. Cool. What's the moment of a mass? You know what I mean? Moment of a mass. Well, that's mass. That's mass times distance. That's kilograms times meters. You know what I mean? So what's the mass? And that is mass moment of inertia. Aren't those two things? Well, no. This is, anytime you have moment of inertia, it's the second mass moment of inertia. And so the second means that you take the mass in kilograms, take the distance in meters, but then you have to square it. You know what I mean? So that's what you're getting at. That's why labeling this as just inertia or even mass moment of inertia, it's the second mass moment of inertia. Just like a moment is not a second, this moment of force is not a second moment of force. A second moment of force would be F times D squared. And I think this is a good place to start, because at least I'm familiar with the term. You know what I mean? Where a lot of people teaching this won't even go back to that ever or at all. And the crazy thing about this mass moment of inertia is it's based on the concept of angular momentum. And I think this term can confuse the basics of angular momentum. And I think the second you write angular momentum, well, what is just linear momentum? You know what I mean? And so just momentum, just as a term, is like, hey, I got a mass and I have some sort of speed. Mass times speed. Angular momentum, I mean, it's good to know that it's a cross product if you know what cross products are. But take a point, and then, hey, this does have a mass, and it does have a velocity, and then so I'm going to, hey, take the distance to it. So now I have a distance, we're just going to call it r, we're going to do polar coordinates and stuff. But now the angular moment of inertia, well, it's r cross, and it is p, so this is the term p. Linear moment is p, but it's just r cross mv. You know what I mean? And your mass ain't changing, so it's just a cross product between the radius and then the velocity. Cross product, back to statics, this doesn't get taught enough, you know what I mean? Even I just don't want to even say a word. But anyway, no, you have to. Cross product, is like torquing a wrench. So if this is my wrench, and I put a force that way, hell yeah, we're doing things. You know what I mean? Force times distance, nice perpendicular force. Now the way to really mess this up is to try to turn a wrench by putting a force that way. That would be the actual opposite way to try to torque this wrench, and it ain't going. You know what I mean? It ain't. There's no, you know what I mean? So what we say with cross product is this D cross F is I mean, it is df sine of the angle, you know what I mean? And so sine of 90 is 1, so that's just going to be d times f, and that's what we would expect. Now this one, the angle is 180. No, I apologize. The angle is 0. You know, well, sine of 180. Whoops, I got to get into degrees. Sine of 180. No, yeah, I don't know why I just had a lapse. Obviously, sine of 180 is the same thing as sine of 0, but now you have df sine of 0, and that's just 0, you know what I mean? There's cross product by using angles, but at the end of the day, yeah, cross product is just like, hell yeah, you want a 90-degree angle. You want a moment. You know what I mean? You want force times distance that's going to generate, you know, a turning motion, a moment motion. Alright, my camera overheated. I took a little break, so hopefully it didn't miss anything. We're going over angular, you know what I mean? What is angular momentum? You know what I mean? It's momentum measured from a distance. It's like the torque of momentum. Hey, you got mass and velocity, hell yeah. And then, you know what I mean? If that's going to act around a point, booyah, you have angular momentum. And so, well, let's just, an angular momentum is L, and that's the letter for angular momentum. P is the letter for linear momentum, little p. So we have capital L. Again, it's going to be the radius times the mass times the velocity. So you go RMV. But now, when we talk about angular momentum, we want to be talking about, hey, things rotating around a point. And so we use angular velocity, and this is going to be in radians per second, and there's a bunch of these. Like arc length is in radians, you know what I mean? So if I have a circle from there to there, that distance, the linear distance is the arc length, and then so that's in radians. Angular velocity is radians per second, and then alpha, this is radians per second. It's the angular acceleration. It's the change in angular velocity, this omega, for every unit of time. Okay, so from that, I use the axiom that radians times radius, because how the hell do you get arc length? Well, arc length, whoa. I apologize, this was a mistake, So an angle is in units of radians. So if I have that many radians, then so excuse me. So this angle is in radians. So we have angle in radians, angular velocity, and angular acceleration. But if I take that angle in radians times the radius, I get something normal, and that is going to be arc length. So this is radians times radius, and why is that? Is because 1 radian is about 60 degrees, and the reason is that's 1 radian is because, hey, look at this radius. If I had a string and I draped it around the circle, I'd probably get to about there, and so we're just by definition saying, hey, that is 1 radian, because 1 radian times radius is going to be that length, this arc length. So there you go. So that's arc length. Radians times radius, omega times radius, so radians per second times radius, this is velocity, and alpha times our angular acceleration. Radians per second times radius is something normal, and that's just acceleration in that direction. Okay, so we see that velocity is angular. So yeah, we're trying to get this in terms of angular velocity. So we see that v is angular velocity times r. So you have this term for angular momentum. It's r times m, and then v is r times omega. Okay, hell yeah. So now you get this, And this velocity, this was r omega. But then from this angular momentum equation, what they say is just like, well, at the end of the day, sometimes like, hey, your angular velocity is constant, or sometimes that's just all we want to find. So we're going to lump all these things together, and this is going to be mass times radius squared omega. And then they're lumping this and then just giving this a physical property that's called moment of inertia. And it's true to its name, the second moment of mass, or mass moment of inertia, is you have the mass right here and then you have the distance squared. So there you go. So angular momentum is I omega. But I think it gets a little bit confusing because this I part has a portion of the actual velocity of that mass. So if I have a string and then some mass around a pivot, and I'm going to say, hey, it's got some sort of velocity and a radius and a mass, then I know it's it's momentum. Its linear momentum is mass times velocity. Its angular momentum is times that distance. But now I'm saying, I'm going from here and saying that the angular momentum is also mass, the second mass moment of inertia times omega. So I just think sometimes it's just a hard jump. It's an easy jump to see, sure, I have some sort of mass and it's got a velocity and I'm analyzing it at a distance because it's kind of like a torque. It's got a moment. It's the moment of mass. Like, hey, it's a distance. So angular momentum is the first moment of momentum, of linear momentum. It's the moment. It's the momentum, mass and velocity times a distance. Just like a force moment is force times distance, acting at a 90-degree angle. Angular momentum is mass and velocity times the distance acting at a 90-degree angle. But we just know that this velocity also is omega times r. And then so you get the second r piece, and you get rmrv, and that's omega, and then you get mass radius squared omega. And now we're saying that this is its own property, second mass moment of inertia, or just moment of inertia. Okay, so now where do we want to go from here? I'm just kind of learning, as I go. But if I can't put words to this correctly, I don't even care if I put words to it wrong. I'll correct myself in a few days. You know what I mean? But it's just a matter of like, hey, if I can't spell it out and keep making sentence after sentence, then it's either taught wrong, or it's just too confusing, or there's not enough back to the basics. So what we're going to do is we're going to analyze this. So at the end of the day, we're going to... so this is the other aspect that I do not like, is you have this in statics. Hey, you're summing the forces is equal to mass times the acceleration, and usually acceleration is 0 for a bridge. We're analyzing a bridge and we got some force on it. It's not moving. And so the sum of the forces, this P down has to be equal to P divided by 2, usually P divided by 2 up. Like, hey, it's nice and balanced. If we don't have balanced, then we have velocity. We have a change in velocity in a direction. We have acceleration. This acceleration isn't 0. And in that direction, let's say this is the y direction, we would have acceleration in the y direction if this was unbalanced. But then we have this term of like, hey, I want to come to this point A, and I want to sum the moments. So this is L divided by 2, this is L divided by 2. And so if I sum the moments at A, hey, I have a P divided by 2. So I have a positive moment, like, hey, of half this load, but at a distance of L. So I have P PL divided by 2, and that's in the positive direction. Now this one, and the forces acting at A don't cause a moment about A, but this way I have a negative moment of P, but then a distance of only L divided by 2. So now I have minus PL divided by 2. Cool. And for a bridge, those should equal 0. But now if they do not equal 0, so we have sum of the moments is equal to, you know what I mean? What the hell's on the other side of the equation? I even looked through the entire physics book, and I could never find sum of the moments, you know, because we know that sum of the force is equal to mass times acceleration. Could not find sum of the moments is equal to I omega, because they don't like to use this term moment. They use the term moment and couple C, you know what I mean, for statics. You know, exclusively, and I'm just like, that's dumb. Like, I think that's dumb. You know what I mean? I think you should have one parameter, and if you observe motion, well, hell yeah, then you have rotation. I don't like using, because they use some of the torques. They're calling motion, if you do observe angular moment, if you do observe rotation, that's what this would be. If your sum of the moments is not 0, well, hell yeah, you're going to observe rotation. And it was just so funny because I have my way of explaining statics, and if the moments aren't equal, hell yeah, the thing's going to rotate. You know what I mean? Yeah, so here's my quick thing on statics. You know what I mean? If I have this block and it's in outer space, like away from every stars, there's you know what I mean? And then we just apply a force, you know, that direction. Well, cool. It's going to move that direction, F equals ma. And it's going to have an acceleration in that direction. And you're going to have a change in velocity. It's just going to go faster and faster in that direction. So now, but let's say you have a force right here and a force right here. Hey, your forces are balanced. Maybe it's not intuitive whether it's, you know what I mean? Hey, there's no net force in the y direction. Cool. But now, so it's not going to be traveling that way. It's not going to be traveling this way. But this thing's going to hella spin. You know what I mean? So you do have angular momentum. And is because it generates a couple. If this is the length, your couple is or this is your distance of this side, your couple is just pick one of the forces times d. And even this will slow down because, you know what I mean, divvy it up in 2. If this is what you're pinning into outer space, then we're going to, you know, the center right there, let's just say a center of mass, then you're going to have this force over half the distance, d divided by 2. That's going to be a negative. So you're going to have negative force d divided by 2. And then this force, also in the negative direction with the right-hand rule, and its distance is d divided by 2. So now you basically just have a force in the negative, or a moment in the negative direction into the page of just negative FD. But this, you know what I mean? Hey, you would do sum of the moments, you know what I mean? I don't even get in statics. They just say, hey, sum of the moments are 0, let's move on with life. It's just, you can't do that. You know what I mean? If the next thing that you're going to learn is dynamics, you have to have an equation that says sum of the moments is I alpha, or, you know, at least something on this side. But they don't. They reserve using moments for statics. And they say if you do have motion, we're going to call it sum of the torques. You know what I mean? And it is like the same stuff in material mechanics, where you're just like, cool, this is the strength of a material, but guess what? Only in the compression, only in tensile or compression, but it's not in shear. You know what I mean? You can't just use this term and then put an S and say, hey, that's just going to be the strength and shear. No, you have to come up with some whole other letter, and I think it kind of confuses the learning process, because you were so ready just to be like, hey, some of the moments now aren't 0, so now what the heck they equal to? And then the text say, well, we kind of reserve moments and couples for statics problems. And I'm probably not 100% on that. I just found in this physics book, you know, they call it sum of the torques. So just right here, you're going to get, hey, sum of the torques is equal to I alpha. Sum of the torques, I alpha. All right, so now we have, so cool. So this equation gets generated from, hey, the sum of the torques is equal to I alpha, And then so we can find angular acceleration. Angular acceleration is just going to be the sum of those torques divided by the moment of inertia. But what we're going to do to finish up this problem is, and hopefully soon, is to show that we don't have to analyze this with using a moment of inertia term. Like, that's my goal, is to turn any problem that has rotation and make it simple. Like you just never knew this moment of inertia existed. Because equations will just always just go right here, but you lose the basic understanding of what's causing rotation, and heck yeah, so let's do it. So we are going to say that, so now I'm going to maybe use circles. So now, and then here's a string, and then here's the mass of the father. Okay, so in this situation, if we just have air and space, well, it looks like this is going to have a weight or a force down of mass of the father g mg, and then so at this point, you know what I mean? If we use F equals ma, we have forces in the y is equal to mass times acceleration in the y. And for this, we can rearrange acceleration in y as forces in the y divided by the mass. The mass that we're analyzing is the mass of the father. The force is mass of the father g. So we get mass of the father g divided by mass of the father, and we get an acceleration of g. I think we can see that. But now from the scenario that we don't have a string, we still have a pivot point of the middle O, but now we have some other weight over here, and now we're just going to say, hey, this is a carbon fiber, it's just really lightweight. It's something that connects them, it's stiff, it is a teeter-totter, but its mass is negligible on this. So this is going to be the mass of the daughter, and then we have the mass of the father. So now right here is kind of where I wanted to use that bridge analogy. Is that, and I guess, you know what I mean? If these were equal, it would be balanced, and I guess it's the opposite. Yeah, that's where I was trying to go with it. Maybe it's the opposite. I have no idea about the bridge analogy. But if you have a load P, well, sure, right here is going to be P divided by 2, P divided by 2 if you have equal distance. Now, you could flip this thing around, and let's do that. Let's say you have the load P this way, but now you have, you know, like down here, you have P divided by 2, and then P divided by 2. So that's what we have for the teeter-totter. Okay, cool. And then so we have a nice balanced, it's totally balanced. So now let's do that scenario where it's unbalanced. So we have the middle of the teeter-totter, and let's put, we're going to put and let's just put like, hey, let's just put like your hand on this side, and then you have to push down on this. So now I'm just going to load this up. And then we have L divided by 2, L divided by 2. But let's say I put, I'm just gonna move to pounds. Let's do like 10 pounds. So if I put 10 pounds right here to make this thing balanced, what do I have to push down with? Well, I have to push down with 10 pounds. Cool. Yep. And let's go back to the problem, and then so the daughter weighs 50 kilograms times 10 meters per second squared. The weight is mass of the daughter times gravity. You know what I mean? So it's 500 newtons divided by 4. It's just over 100 pounds. But we have 500 newtons of force down. To make this balanced, I would have to put 500 newtons to hold that down. So now in this scenario, we just kind of reverse it. We say the father weighs 1,000 newtons, and that's going to be a downward force. but then the daughter gets over here and weighs 500 newtons. And so we have the force of the father, and then we have the force of the daughter up. So this is 1,000 newtons down, and then 500 newtons up. And then so we have, so now we can go back to this scenario and say, oh, okay. So if we just chisel out the mass of the father, well, we do have the weight down, but now we have a force up. That's the weight of the daughter. That's mass of the daughter G. So now that's what you're going to be experiencing. So we'll still have a net force down. And heck yeah. Now this scenario brings up the same problem that we just had with the pulley. Is like, sure, you can do this and say, hey, I have 1,000 newtons down, and then over here is something leveraging me up. That's 500 newtons, so it feels like I weigh 500 newtons less. But now when we want to figure out if we use F equals ma of this mass, so now we're kind of getting good at this, or maybe not, maybe it's not intuitive still. But we have this 1,000 down minus 500 up. But now we're finding the mass, and what is the mass? Well, it's actually not the mass. So maybe I'm doing a bad job of saying, hey, if I take this free body diagram, that I have 1,000 down and 500 up. I do not have that. It's the same misrepresentation of this, saying, oh, if I take that free body diagram, I have 500 newtons up and 1,000 newtons down, when no, you have 666.6 newtons up, because that's going to be the tension. You have the tension in the rope, not just the mg of the daughter. But yeah, so that is the same, but at least we can kind of get there, intuitively, to be like, okay, I have 1,000 down and I'm getting leveraged up by 500. I want to use a very basic F equals ma equation, but when I do, I have to say that no, this mass is the total mass of the system for that. So I'm going to have we're going to do this F equals ma in the y direction, and we're going to find our acceleration in the y. So we're going to have 1,000 newtons minus 500 newtons is equal to, well, now it's going to be the mass of both. So that's 100 plus 50. That's in kilograms, so it's 150 kilograms times the acceleration in the y. So now we can say acceleration in the y, this is 500 newtons divided by 150 kilograms. And so we get 500 by 150. Hey, we get that same thing. We get 3.33 meters per second squared. So that's pretty cool. And so that was about it. Just a huge roundabout way to go through it and be like, well, what's the simplest way to analyze this? But when I did analyze it, I made this mistake. I said, well, it must be, I'm going to take a free body diagram of that, and I'm going to put 1,000 newtons down, the daughter pulls 1,000 newtons up, and then here's my mass. And that's wrong. You have to take the mass of the system, and now I kind of have a more intuitive understanding. It's obviously not textbook worthy, because at a certain point, even in this, I'm making an error, but it's just not obvious. In this problem, if I take a free body diagram of that, it's I actually don't even know how to take a free body diagram of this one and showing the forces. I can see the mg down, but then because this is a rigid bar, oh sure, yeah, I get a shear. I must get a shear force up or something like that, or do I get a moment? I forget. But anyway, all we're doing is trying to find very basic ways. So if we do problems like these some more, we won't make tragic errors, and we'll get closer to the solution. Man. And so, how do we relate this acceleration that we found? We kind of found the linear acceleration, that if they're balanced, this father is going to be going that way at 3.33 meters per second squared. That's going to be the acceleration. And angular acceleration, again, what the hell is angular acceleration? Well, it's radians per second squared. And like I said, we take radians per second. Anytime you have anything with radians times radius is something normal. So that's going to be just the acceleration. So if we know the angular acceleration, and then I want to know the acceleration of the father at this point, well, I take the angular acceleration times the radius, which is L divided by 2, and then that's going to give me the acceleration. And so we're going to finish just with that and show that, sure, that this is the equation for that. Well, maybe I should have done one step farther, and obviously, yeah, no duh. So let's what I just explained was, hey, sum of the moments is equal to I alpha. So let's start there and then finish with this one. Or we'll finish with this. So let me just get to this. We can do this one real fast. If this is angular acceleration and I want to find that just the acceleration kind of in the tangential direction of the dad, then I just take this times the radius. And the radius is L divided by 2. Cool, there's an L, there's an L, there's a 2, there's a 2. And now my angle is 0, so cosine of 0 is 1, so that just becomes 1. I'm saying that the mass of the teeter-totter is carbon, and it has no mass. So even though that this had an I in it, and they're saying, hey, the moment of inertia, and I should actually at least show you what the hell the moment of inertia was for the problem. Moment of inertia was 1/2 ml squared plus the mass of the father times the radius squared, mass of the daughter, radius squared. And in both cases, the radius is L divided by 2. For the mass moment, second mass moment of inertia, or moment of inertia of a slender rod is just 1/2 ml squared. But you know what I mean. I would derive that every time if you don't know where that comes from. That's the crazy thing about using, this letter I, is that if you don't derive it each time, then, you're not going to have an understanding. Now, I get some things, like if you have the area of a circle, that's 2 pi r. Like a circle never changes. It's always the same. There's never like, hey, like, oh, well, that's different, and you have to use a different equation. You know what I mean? That would be like 2/3 pi r squared. Or, I'm sorry, pi r squared. What the hell is the area of a circle? Pi r squared. But yeah, using the I, if I was just a term that was just, like pi, like the same for every scenario, but it's not. It's completely different for every different scenario. So you look up in the textbook, like a hollow tube, like a full sphere, a sphere that's just a shell that's like hollow on the inside, a disc, just a solid disc, a hoop that just has the mass on the outside. All those have different moments of inertia, and they cause a different solution to the problem. And it's not going to be intuitive why, if you don't derive those each time or have an understanding, or you know what I mean. And maybe you don't. Maybe you can just do a few problems and see that point masses have moments of inertia of mr squared, and like what, a disk? Is a disk, is that just 1/2 mr squared? But sure, it has less, because a point mass, like on the exterior that's whipping around, it is already on the exterior. Its mass is as far away, and if we're saying this is the radius squared, this mr squared is maxed out. Where if you have a disk, hey, just these chunks of mass are near r squared. You know what I mean? But all these chunks of mass aren't. So you're going to have a lower value. And when you sum across that entire thing and find all those, hey, it's just half. Don't quote me on that, but I think, yeah, isn't it just like a disk is 1/2 mr squared? And then, yeah, a sphere. Sure, it's like 5/2, I think. No, don't quote me on that. I think it's 2/5. Like, yeah, obviously anything, yeah, even just the fundamental understanding of mass moment of inertia, unless the mass is at its extreme of radius and it's just all out there, then you're going to have something less. So a sphere, hell yeah, a solid sphere is 2/5. That's less than a half, you know what I mean, mr squared. So it's worse than a disk. And theoretically, you can show that, because if you have a sphere, all your mass is bulbous, and so if this is my sphere rolling down, like all the mass is like near the center, you know what I mean? Where that's the opposite of putting the mass at the extreme, like on a string, mass and radius squared. So if you're trying to find mass radius squared, well, all your mass, there's a large portion of your mass because it is centered around the center in the long way, you know what I mean? And then only a portion. Even compared to a disk is just as thin in the center as it is at the top. And so, hell yeah, you get more proportion of your mass at the outside. But that's my take on moment of inertia, and it just has to be unnecessarily complicated. And when you use it, you just lose all sense of kind of what's going on with the problem in terms of F equals ma. Now that's all right. If you use the energy equation, you lose all sense of what the hell is going on with the problem in terms of F equals ma. But it makes the problem a lot simpler. So my goal is to, anytime I can, where we're going to analyze a problem using F equals ma, because that's just the hallmark of physics, especially Newtonian physics. All right, so heck yeah. So now that in a nutshell is why we crossed this out. But this term is still in terms of mass moment of inertia. They took the torques off the top, which we figured that's the part that we're going to figure out in the next thing. Is just the mass of the father times the they already pieced everything together. I'm sorry. This equation is after they simplified it, because torque is going to be a force, mass times gravity, but times the distance. So it's going to be times L over 2. But then this moment of inertia already has an L over 2 squared. You know what I mean? So now your L over 2 squared becomes L, and then your top. So I apologize, I'm not going into that. What we're mainly focused on is just, hey, we just solved this thing. We found the acceleration as 3.33, and how does that relate to angular acceleration? Well, angular acceleration times radius is this normal acceleration. So this should be 3.33. And so all we have to do, again, was to take L divided by 2, that's the radius, L divided by 2, times angular acceleration, and then we should get 3.33. We already crossed out the L's, we crossed out the 2's, we said that the slender rod has no mass, we went on the tangent of talking about mass moment of inertia, or second moment of inertia, or just moment of inertia. And then cosine of the angle is 0, because all we want to do is analyze it right at the balance point, and then we want to see how fast this, we want to know the change in velocity, change in time. You know what I mean? Hey, we know this is going to have motion, change in velocity, and that's the definition of acceleration. So booyah, we're going to get acceleration is mass of the father, 100 minus 50 times gravity, 10, divided by mass of the father, 100 plus 50, and we've seen this before. It's going to be 50 divided by 150 times 10, and that's going to be 3.3. So 100 minus 50 divided by 150, and that's going to be times 10. Sorry about that. Is 3.33. So now I am going to finish this problem by saying, hey, sum of the moments are going to equal I alpha. And so now we're going to have the mass of the father, a pivot point, and then same distance but mass of the daughter. L divided by 2, L divided by 2. We're going to sum the moments about O. And so we're going to sum the moments about O. Like obviously we have a mass father G, and then here we got a mass daughter G. You know what I mean? That's the weight. These forces exist. We identified a mass, and because the Earth is underneath us, force of gravity is gravitational constant, mass of what we're doing, mass of the Earth, radius of the Earth squared. So we have identified a mass, that's mass of the father, so we know the force of gravity. There is going to be a force on that. Okay, so now we use some of the moments. We pin this, and then we say, hey, we have a downward moment, and this is equal to I alpha. So we have a downward moment, negative mass of the daughter G times L divided by 2. Okay, now this one's going to be a positive moment, plus mass of the father G L divided by 2 is equal to I alpha. And then what the hell did we say alpha was? Alpha is in radians per second, and then so alpha times r, radians per second, anything with radians times radius is something normal. It's going to be the acceleration. But for this, we have to pick the radius that we're finding. And then, just like the Pulley problem, the acceleration at this point upward is going to equal the same as the acceleration at this point downward. So that's the cool thing about things that are pivoted and spinning. You know what I mean? It doesn't matter what the masses are. That's why it's similar to the Pulley problem, because the mass of the entire unit is important in its in the setup. Okay, so we're gonna so all we have to we can replace this alpha with A divided by R, which is A divided by L divided by 2, which is 2AL. So now we can put this over here as, did we even want to do that? Oh, no, not really. I mean, at the end of the day, we just wanted to find the moment side. You know what I mean? So cool. We have negative 50 times 100 L divided by 2 plus 100 times 10 L divided by 2. So at the end of the day, we have 50 times 10 L divided by 2. That's going to be our moment, and that's going to be equal to I alpha. And we were saying that alpha times R is acceleration. So if we just wanted to find oh shoot, yeah. Oh yeah. So this alpha term is going to be the acceleration we want, but we have to divide it by the radius. So there you go. So that's acceleration divided by L divided by 2. So we can do that. So we have 50, 100, L divided by 2 is equal to moment of inertia, acceleration divided by L divided by 2. And then so we have this up top, this downstairs, so we can cross that out. So now we have 50, 100 is equal to the moment of inertia times A. So I don't know. You know what I mean? That's why I just wanted to get there from a fairly Newtonian and not using angular momentum. But yeah, I see that some of the moments you still have this moment of inertia term that you have to figure out. And the moment of inertia for point masses, that's going to be the simplest, because and, you know, if you see this moment of inertia term, just think angular momentum. So if I do have a point mass that's a distance r away, then the angular momentum of this is going to be the mass, velocity. This is bumming me out. No, I guess I'm fine. Yeah, it's good to do this. So if we do have some sort of velocity that way, it's going to be the radius times the mass times the velocity. Velocity is angular momentum, angular velocity times r. So we have r m r omega, and this is m r squared omega. And this is so angular momentum is I omega, where the I for a point mass is going to be mr squared. So why I did this is just like this. This will, by definition, tell you what the second moment of inertia of a point mass is from using angular momentum of a mass on a string. But the definition definitionally, moment of inertia is the second mass moment of inertia. Second mass moment of inertia. So you take that mass in kilograms and then take the meters and then square it. You know what I mean? So you have mass radius squared. That is the definition of moment of inertia. And I guess this is one principle. From researching this topic this week, at least I knew that the moment of inertia of a system is, so the moment of inertia total is the moment inertia of the parts. And I guess I get that. If I have an I-beam, this is also the second moment, but it's the second moment of area. Where if I find the moment of area of this, and then add it to that and that, then I have the total. I have I total. This would be the moment of inertia of area. So it would be distance. It would be a distance squared for all those things. And sure. So now I know the moment of inertia of the total system is going to be the mass of the father times the distance, L divided by 2 squared, plus the mass of the daughter, L divided by 2 squared. And and that's going to be equal to A. All right, hell yeah. Last push. And, oh, I'm sorry, that's going to equal alpha. So I'm going, let's go back to this one, you know what I mean? Because I didn't want to take that shortcut. We have the moments, we just summed them. That's our moments, and that's going to equal I alpha. The I is going to be this thing, is going to be the mass of the father, the distance squared, plus the mass of the daughter, distance squared. So that simplifies to L divided by 2 squared times mass of the father plus mass of the daughter. And that is going to be equal to our I. And now that's going to be equal to our angular acceleration. And then again, we can say that, hey, we just want to find the acceleration at the extreme. So that's going to be angular acceleration times radius. Radians per second squared. You know, radians times radius is something normal. So we got acceleration. And so, booyah, this becomes the acceleration times L divided by 2. Holy Toledo. No, my apologize. If something normal is alpha times r, alpha itself is the acceleration at something normal divided by the radius, which is L divided by 2. So this is acceleration divided by L divided by 2. So this cancels one of them. And then those cancel on both sides. And I apologize, I'm just running out of room here. But now we did it. We have what the hell did we even do? We have 500 is equal to mass of the father, mass of the daughter. Huh. I feel like we... Oh, whoa. No. We still have one term in here. I apologize. I'm just getting all messed up. We still have this term acceleration that we were solving for. That was the whole point. Using moments is equal to I alpha to solve for acceleration. Knowing that alpha times radius is acceleration. And then so acceleration... or that alpha is equal to A divided by R, and that's going to be A divided by L divided by 2, and then I has an L squared term in it, and then yeah, so one of those cancels, and if one of those cancels on this side, it cancels the 1 on that side, and now you have 50 times 100 is equal to mass of the father plus mass of the daughter times the acceleration. So now you have acceleration is just 50 times 10 divided by this 100 plus 50, and you get that same relationship, 3.33. Holy Toledo. But, you know, I don't want to edit this video. Like someone says, hey, do you ever do things from scratch where you just, you know, don't know? Or do you just know how to do it? But this one, I went on a couple bike rides. I thought about it. I did nothing on paper. I just kind of mentally wanted to make the association with the pulley, knowing that I'm gonna make that err a lot and say, hey, the tension in this pulley is just the weight of the other person. But I should know that if I went to the other side, and this was only 500 newtons down, well, then I would say the tension is 1,000 newtons up. Or, I'd have a 500 newtons down and then 500 newtons up. Wait, how would that work? That would still be a... Oh, no, that would be the tension. So in one scenario, my tension is 500 newtons, and in the other scenario, my tension's 1,000. And then by continuity, because these things... And it's continuity that the whole mass is the total mass, that the tension in the cord is 666.6 newtons for that problem. But heck yeah. And but now after making this video, I should be able to... get there a lot faster, do a lot more rotational problems, and be even able to find creative ways to make them simpler. I think that is a must for all rotational inertia problems. Anything with angular momentum, just basic ways to find ways to make the problem simpler, just so then when you get into the complexities of using second mass moment of inertia, there's so many places for little errors, and you just don't know if you're gonna get the right answer or not. So just having some way to make a problem simpler, so you can have an intuitive sense of what's going on, is very useful. All right, thanks for joining me for this one, and guess what? That's a video.